Okay guys, so welcome to back to the end of mechanics now, and this section is I'm going to do, at least for the first sort of few learning timetables, I'm going to do a video attached to each one of these, so you get for your homework your 3 questions a week. And from the AS chapter, what I'll do each week is give you 3 different questions, so all the work that we've covered in this AS series, mechanics series, we'll have questions from all of those, and just to get you the practice with those. Just to ease you into it, done them in the same style as a normal learning timetable, except only 3 questions, Sunday, Tuesday and Thursday. So have a go at them, put this on pause, and do the questions first, and then you've got this to watch and support you as you're just starting off on your mechanics sort of practice. Okay, so here we go. The first one, you've got the sheet that you can download, but the first one is that a particle is acted on by two forces. So the first one, it says force 1 is, these are, by the way, as anyone else is watching these videos, the reference here, question 2, May 2009, is from the Edexcel M1 paper. These are all M1 questions. Okay, so F1 is I minus 3j newtons, and F2 is pi plus 2pj newtons. Find the angle between, so A is find the angle between F2 and J. Okay, so let's do part A. So let's do there's our J axis and our I axis. So I is along and J is up. And F2 is pi, so it goes along pi and it goes up 2p. There's 2p, so that's where it is, that's the position of it. So as a vector, let's do it in a different colour. There it is, that's the vector pi plus 2pj, that's the vector F2. And it says the angle with j, so it means the j axis, it means this angle here. Okay, so let's call it alpha. So if you look at that, if we dot across, because normally we find this angle here, but if we dot across so we can find this angle directly, you can see you've got a right angle triangle. That distance from there to there is p, and that distance there up there is 2p. So basic trigonometry, opposite over adjacent is tan, so the tan to the minus 1 of alpha is opposite over adjacent from GCSE trigonometry. Okay, so tan to the minus 1 of and we want opposite, so p over 2p, and the p over 2p, the p's cancel, don't need to leave you with a half, so we want the inverse tan of a half. So we get our calculator, shift tan 0.5 equals 26.6 rounded off, so alpha must be 26.6 degrees, and it looks correct to me. Just checking that that's in shot, and it just is. Yeah, okay. So it says the resultant of F1 and F2. So there's F2 and F1. Remember, the resultant means when you add the 2 forces together. So, you know, there's the particle, you got that force acting on it, and this force, which is I minus 3j, so that's 1 along and 3 down, so it's going in that direction. So that's that force there. So those 2 forces are acting on that particle. The resultant of those 2 forces is when you add the 2 forces together. So that's one force, that's F2, that's F1, and the resultant force, you know, is the, you know, from the start of one to the end of the other. Okay, so that's what we're trying to find now. Okay, and it's saying the resultant force of F1 and F2 is R, given that R is parallel to I. We'll talk about that in a minute. Let's find that resultant force first. So B. So the resultant force, of course, is those 2 added together. So let's do that. So I minus 3j plus pi plus 2pj. Now let's get all we always do the same thing here, get your i's together, get your j's together. So we've got I plus pi plus, and I'm going to put the 2pj there, minus 3j. I could have done it minus 3j plus 2pj, but just to keep it positive, So I've got my i's at this end, my j's at that end. I'm going to factorise and take out my i's. So when I take out my i's from this, I've got 1 plus p, haven't I? Lot of I plus 2p minus 3j. And there you have it. Okay? Any vector in terms of I and j is amount of I and amount of j. Amount of I plus an amount of j. So along that much I and up that much j. That's our resultant. Okay, written in its best form. I've got my cup of tea here, sorry. Okay, so what's this saying? It says this resultant is parallel to I. Well, if it's parallel to I going in that direction, then it's got an I component. It means that the j component is 0. So all of that is 0. So 2p minus 3 is 0 if it's parallel to I. And likewise, if the question had said it's parallel to j, then the I would have been 0. But because it's parallel to I, okay, it has an I component, but it doesn't have a j component. So that must, so 2p minus 3 must be 0. And so you can see there that p is 3 over 2 or 1.5. And that's what the question is asking, the value of p. Okay. All right, that's the first one. Hope you got that. Every question that you get on equations of motion, throwing balls up or stones up into the air, okay, so always draw your diagram first of all, please, and then put your values on. It just makes things a lot easier, and that's what I'm going to do. So I'm going to read it through first. A ball is thrown vertically upwards with a speed of u meters per second from a point P at a height h above the ground. The ball hits the ground 0.75 seconds later. The speed of the ball before it hits the ground, in other words, it means on impact, is 6.45 meters per second. The ball is modelled as a particle. Okay, so our diagram, there it is. There's the floor. Okay, that distance there is our h, and our particle starts from here, and it goes up, and it comes down, and it smacks the floor there. Okay, so we don't know that height, it's not told us that height. So there's our diagram. Okay, that's the starting point. And there's a few things we're going to have to find. We're going to have to find u, the initial velocity, meters per second to the minus 1. Things we do know. We know that gravity, we're going to say up is positive, so we've got to be careful here. Gravity, you know, we're going to put in as minus 9.8 meters per second squared. So that's a downward pull. So it's going to be decelerating and accelerating, but it's minus 9.8 because it's pulling it down because we've decided up is positive. And this is the important bit here, okay? The time at this point, not this bit, is 0.75, but this, it says the speed that it hits the floor is 6.45 meters per second, but this speed is going that way, it's going down. So in our equations here, the velocity, we've got to put it in as minus 6.45. If you don't do that, you're going to get it wrong. Okay, so it's what we said, going back to those equations of motions, you have to choose your direction, okay, before you start sticking numbers into formulas. All right, so this first one, show that u is equal to 0.9. So A, show that u, so don't stick 0.9 into formulas and show that they balance. Work u out itself. Okay, so we've got to show that u is 0.9. So here, what information have we got? We've got a velocity and a time, and we've got an acceleration. And we only need the initial velocity. So we're going to use v equals u plus at. We know that the velocity is minus 6.45. We don't know the initial velocity. I'm going to find that. Plus, and we know that the acceleration is 9.8, and it was this velocity at a time of 0.75. Okay, and so if you multiply that out, okay, and then add, you get minus 6.45 is equal to u minus, well, I'm going to do it, 9.8 times 0.75 is equal to 7.35. add 7.35 to both sides, you get u is equal to 0.9. Okay, that's meters per second to the minus 1. All right. B, the height above P to which the ball rises before, you always get this in every exam question, you always get this. So the height above, so it wants the height above P. P is the height of this tabletop or cliff top or whatever. So it wants this height here. Okay, so we're going to say here for this, we're going to say at this point, this is the point s equals 0. Okay, displacement is 0, that's the starting point. So this point down here is minus, and we want this positive value up here. There's something that we know that's special that allows us to always work out the time to the highest point or the distance to the highest point, and that is that the velocity at this highest point is 0. Okay, so it slows down, it stops instantaneously and then speeds up coming down. So at this point, it's a special point in a stone or a ball's journey, is when it's been thrown up, is that the velocity at the top is 0, okay, as it turns to come down. And we use that to great effect to find the time to the highest point or the distance to the highest point. So let's find the distance to the highest point. So the distance to the highest point, we want an s in it, so we don't want to use, we'd use v equals u plus at to find that time. We could then put the time into s equals ut plus half at squared, but we're going to go straight to v squared equals u squared plus 2as. That gives us the answer straight away. The velocity squared, so we want to find this displacement when the velocity is 0. So 0 squared is equal to, now we know that u is 0.9 because we found that, so 0.9 squared plus 2 times acceleration is minus 9.8 times s. Okay, so 0 is equal to 0.81 minus 19.6 s. 19.6 s is equal to 0.81, and s is equal to 0.81 divided by 19.6. No, not very high actually. Divided by 19.6 is equal to 0.04. Now it didn't have a very fast initial velocity, only of 0.9 meters per second. So actually it only goes up 4 centimeters. Okay, it slows down very quickly. It only goes up 4 centimeters. 4.41 that is. So it's 4.1 centimeters. Yeah, so it only goes up 4 centimeters before it turns and drops down to the floor. Okay, so that's that one. Hope that fits in. Yeah, it does. And then the last one, find the value of h, this distance here. So all I'm going to do for this, for C, is just use s equals ut plus a half a t squared. Again, just checking that fits in, and it does. Okay, because we're using gravity, on every one where you're throwing something vertically up, and gravity is minus 9.8, half of minus 9.8, of course, is minus 4.9. So we can do minus 4.9 t squared. We can use that one. Okay, now we know that the initial velocity is 0.9. We know that it takes what am I doing? Oh yeah, we want to find the displacement after this time, don't we? Because at 0.75 seconds it's at the bottom here, and that will tell us this displacement here at that time. So times 0.75 minus 4.9 times 0.75 squared. That's probably just gone off your screen. Okay, yeah, that's okay then. I'll shifty it along there. S is equal to 0.9 times 0.75 minus 4.9 times 0.75 squared. Okay, and that should just fit on now, and it does just. Okay, and of course the s, it should come out negative. If it doesn't, we've done something wrong. And the minus just means it's down this way and not up that way. Okay, so that's what we're going to put into our calculator. So 0.9 times 0.75 minus 4.9 times 0.75 squared is equal to, and minus 2.08. One, 2, 5. Let's round that off. Okay, so the height is equal to 2.08 meters, 2 meters and 8 centimeters. Okay, that's the height above the ground that it starts. Okay. Thursday's question, I left that in. It's from the old M1, and don't worry, I have found other questions on variable acceleration that wasn't in the old M1. So, and I have included those in subsequent learning timetables as well. So you're getting a look at all of the stuff from the AS book. But on Thursdays, it's got this acceleration time graph. Now they used to be on the old syllabus, but they're not in the new AS book. But I think it's good for you to see this anyway, and think about it. You might be able to work it out for yourself, but I'm going to go do this one for you. Okay, so I hope you've had a go at it, and you're looking at a strange looking graph for this one here. But anyway, let's do this one. A car accelerates uniformly from rest for 20 seconds. It moves at constant velocity v meters per second for the next 40 seconds and decelerates uniformly for 10 seconds until it comes to rest. For the motion of the car, sketch 1, the speed time graph, and the acceleration time graph. Okay, so let's do A. So part 1, the speed time graph. So that's a velocity time graph. So we want the velocity and the time. Okay, so what happens? A car accelerates uniformly from rest. So constant accelerates. So rest is important. It means its velocity was 0. And after 20 seconds, so there's 20 seconds on our timeline, it's accelerating up to that. Okay, I like to do little dotted lines in here. You're doing this on the exam. I always tell my students to do to use pencil and ruler for these. Look at the sketches, make them look decent. 20 seconds. It moves at constant velocity, so that's that velocity. So constant velocity for the next 40 seconds. So that point there is now 60, isn't it? Because that distance there is 40 seconds. We can put that in if we want. That distance there is 40 seconds. And then it decelerates uniformly for 10 seconds. Okay, finishing the journey 70 seconds later. There we go. Now you can work out the gradient here of these and work out the acceleration and that. Actually, you can't without V. Ignore that. But anyway, there's our velocity time graph, and that's done. That's all you can put onto that for the moment. Okay, we'll do part 2. The acceleration. These are weird, these. Okay, and there's acceleration time. Now you can see I've done a negative here because what's happening is that a positive acceleration is going to be above the x-axis and a negative acceleration is going to be below the x-axis. And this one here, so it's accelerating for 20 seconds. So there's our 20 seconds. Let's put the sections in there. Those are the 3 sections. Try to line them up. So this acceleration we can't work out, but it's a positive acceleration and it's constant. Okay, so for the first 20 seconds it's constant acceleration, like a constant velocity was. In this one was a straight line. A constant acceleration is a straight line. It's not increasing its acceleration. It's not variable acceleration. Okay, so it's a constant positive acceleration. And then and it does that for 20 seconds. The next 40 seconds, it's then just a constant velocity. So the acceleration, the person has put the foot on the accelerator, speeded up, you know, and suddenly when they've reached a speed, they've stopped accelerating. So the acceleration is 0 at that point, isn't it? Okay, so it's not accelerating anymore. Okay, for the next 40 seconds. Okay, so that is 0 for the next 40 seconds. And then for the last 10 seconds, it's decelerating. So if it's decelerating, it's a negative, and it's constant deceleration, so it's a negative. And it's obviously going to be steeper because it's so that little line would probably be further down here, wouldn't it, if we knew what the figures were. It doesn't matter for our sketch though, for the next 10 seconds. But that's a constant deceleration. It's on the negative side. Okay, so there's sort of naught on both the x and the y axis there. Okay, and you sometimes see these drawn, and you've seen these in old books, these sort of put a dotted line there, because it switches from that instantly to that section, so it's like stepped. And that's describing constant acceleration for 20, at point 20, at point 60, finishing at 70, okay? And then it's back to 0 because it stops. Alright, so that's your acceleration time graph. Now, given that the total distance moved by the car is 880, find the volume of V, and we've done these. So remember, area underneath the velocity time graph is the displacement, the distance covered. Okay, so this, of course, because it's not starting somewhere up here, so we don't have to split the shape up. It's just it's a parallelogram, isn't it? No, it's not. It's a trapezium, even. So 880, that's 40. The bottom is 70, and that is the velocity, isn't it? That there, the height of it is the velocity. Okay, so that's what we're solving, and the area of it, you know, is a half of, you know, a plus b times h. That's the formula for the area of a trapezium. So we've got 70 plus 40, which is 110. Half of 110 is 55. So the area of 880 is equal to 55h. Okay, and then divide 880 by 55. 880 divided by 55 tells us it's 16. So the velocity is 16 meters per second to the minus 1. That's what that is there. So that, if we add it on, completes our velocity time graph. There we go, nice simple question. Quite hard to believe that that is A-level standard, isn't it, really? Okay, alright. Hope that makes sense. Hope you understand that, okay, and it's a good revision for you going back to that, those first questions. Okay.